Okay, today we are going to do something different, not necessarily new, but it's different. And we are going to look at acceleration now. Okay, so we are going to focus on acceleration. So just a quick reminder, term test 2. Will be on November the 6th. Okay, which is a Wednesday. And it will start at 6:30. And we'll finish off at 9 p.m. Okay, the location is, I put the location on Avenue to Learn, but I could not remember where. If we could just briefly go to Avenue to Learn. Okay, so if we go to Welcome, the location is in PGCLL 127. Okay, PGCLL 127. Okay, so there's a location of our term test on Wednesday. Okay, so be there. Okay, those of you, yeah. Right, so today we are going to look at relative motion analysis for acceleration. All these diagrams are posted on Avenue to Learn, if you could get them. Okay, so if we have 2 points, okay, we have point A and point B, and point A path is at the top, and point B path is at the bottom. And if we look at acceleration, we write it in the form of acceleration at point B is equal to acceleration at point A. Now, the difference is here, okay? So this is plus acceleration B from point A, T, okay? And then we have plus A, B, acceleration of B from point A, and then we have a subscript N. Okay, so that is the difference we see relative from velocity. So let me define some of these terms. So A, a subscript B, is the acceleration of point B. And then A over here, okay, a subscript A, you have acceleration of point A. Okay, and you can see two new terms. Okay, and what it states is A, B relative to A, T, and this is the tangential acceleration of point B with respect to point A. Okay, so in terms of magnitude, A acceleration B from point A tangential can be calculated from alpha R B relative to A. Okay, where alpha over here is our angular acceleration. And this is in radians per second squared. Okay. And then the other term where you have acceleration of point B relative from point A, N. So the N denotes the normal acceleration of point B with respect to point A. Okay. And then its magnitude can be computed or calculated, and you have seen this before. It is equal to omega squared. Hold on. Okay, multiplied by R B from point A. You don't worry about that image first. Okay. So if now we were to go back to equation number 1, can you label this equation number 1, please? Okay. Now, if we can go back to equation number 1, okay, equation number 1 is the first equation that we have over here. Right? So if we look at equation number 1, what we have now, right? I'll just write a form. So acceleration of point B is equal to acceleration of point A plus, okay? So what we have now is alpha. Now, this over here is cross, okay? Alpha cross R, yes. Oh, yes, and thank you. Okay. And then the next term over here is R B from point A. And the next term over here, okay, so this is equal to omega squared R B A. Okay. So over here, this is the tangential acceleration. And over here is the normal acceleration. Okay. So if we were to look into this diagram over here, right? I want you to look at this diagram over here. The A acceleration from point B relative to A, that is the tangential direction. Okay. And over here, you have A acceleration of point B relative to point A in the normal direction, and it's pointing towards the what? The reference. So over here, this is our what? Reference. Okay. And for this reason only, that's why we put a what? Minus sign. Okay. And the full form, if we were to look at the full form of this equation, right? We have to be very careful in this context. If I'm going to write the full form, right? So we know that acceleration at point B has a tangential component, okay, plus by acceleration of point B has a normal component, and this will be equal to acceleration at point A with a tangential component plus by acceleration at point A has a normal component. And then we have plus alpha cross RB from A. And then I'm going to move this diagram if I could. Come on, move. It's okay. No. I do apologize for this. Really, Eugene? Okay, and then this is minus omega squared RB. Okay. Now over here, this term over here is a cross, okay? This is a cross. Okay. When we do an example, it's clearer. Now, from here, we know that AN will be equal to omega squared R. Okay. And note that V is equal to R omega. And from here, we know that omega is equal to V over R. So therefore, the normal acceleration in terms of magnitude, we can put this as V squared over R squared multiplied by R. So this is equal to V squared over. Okay. Right. By doing an example, what I'm writing over here is clear. As I say, this is a cross. This is not times. This is cross. Okay, so it's a vector form. Okay. So let's look at question or example number one. We're going to apply all this into example number one, and example number one is the easy one first. Okay, we're going to do something easy first. Right. So what we have over here is it's a member AB resting on the wall. That's 90 degrees. So at a given instant, the top of NA, okay, so this is our point A, okay, of the bar, has a velocity and acceleration shown. Okay, so we are given a velocity at point A and acceleration at point A also. Determine the acceleration of the bottom B, right? And the bar angular acceleration at this instant. Right. So we know that at point B will slide in this direction. Okay. So we're going to declare this is our direction of point B. This is our velocity. And likewise, we have an acceleration of point B. Okay. So from here, how will this member AB rotate? We know that it's going to rotate in this direction, right? So this is our omega AB. Okay, that is our omega AB. So from here, we're going to write out our equations. Okay, what we can observe is point A and point B. Yeah, we know that we only have one direction only. Okay, so let's write out the formula first. We know that the acceleration of point B is equal to acceleration of point A, okay, plus by alpha cross R B from point A, and then plus by omega squared, right? R B from point A. So now if we were to look at our unknowns, we know that we don't know what is A subscript B. We don't know what is our alpha, and likewise, we don't know what is our omega. Okay. What we do know, again, so given, right, we know that our velocity at point A is equal to minus 5J, and this is in feet per second, right?